This is from a slide from day before yesterday, and we were talking about what we see um, uh, with regard to the spectrum of a star like the sun, for example. And I said that the purpose of the lectures, one of the purpose of the lectures, would be to understand what we see. And so we had this spectrum, which is shown in the right and bottom corner, as you see from the sun, and superposed on it are the black body curves of different temperatures, and it looks like uh, for a wide range of wavelengths, the solar spectrum is well fit by a black body of around say, 5,700 degrees Kelvin. But there are deviations of both kinds. We see absorption lines, which are basically subtracting lines from the black body. As you can see, dips, right? And then there are spikes also, which are emission lines. So we would actually like to understand both. And that's what we want to do today. And in order to do that, we need to understand, and on the top right corner, I had this sketch of structure of the sun or a star, although we have not really talked about it, but we can guess that it's a spherical object, and there's matter and there is radiation, and we realize that the radiation has to leak out from the surface, and that should cause some deviation, because that's going to then disturb the equilibrium there, a thermal equilibrium between matter and radiation, and so it is likely that there is some deviation. Now, these are just words. So I would today I would like to quantify some of these things that we have been saying, and that would probably will make our discussion more rigorous and more precise, and which will help us go forward with building a model, a physical model of a star. Okay. But we should talk about black body, and I'm not going to derive this because you all know black body radiation is, but I'm just going to mention the important parameters. Now, we have already set the language in terms of, we have talked about what specific intensity is. So when we say that the black body radiation curve, this is the specific intensity, and I'm going to write B whenever we have black body in mind. So this B, capital B, is nothing. B new is nothing but the I new we had earlier, but for the particular case of a black body. That's all. So we know the units. So this is energy per unit time, per unit length square, per unit hertz, per unit steradian. We should keep these units and dimensions in mind, so that we know what this parameter is. And as you know, a black body radiation spectrum is of a particular shape, the Planckian spectrum, and this is how it goes, as a function of nu, when it is written as per unit frequency, but you can also write it as per unit wavelength. But then you'll have to do the corresponding change from d nu to d lambda, and you can do that because they are related. Now, as you can see, so the examples of black body radiation spectrum at different temperatures, it's shown on the right, and you are all aware of that. The peak shifts towards shorter and shorter wavelengths as you increase the temperature, and that is known by the Wien's law, the displacement law, and so this is in centimeters. So h nu, sorry, no, this is dimensionless. So h nu max, the energy of the photon at the peak is roughly of the order of kT, say 3 times kT or 2.82 times kT. By the way, you might want to ask the students at this point that when you actually maximize, which means you are basically taking a derivative and then putting it to 0, and that's how you find a maximum. But the derivative with respect to nu and derivative of b lambda with respect to lambda may not be at the same frequency or the wavelength. Okay, so there is a slight subtlety here. When we say nu max means what? The peak with respect to frequency or peak with respect to the wavelength? There's a slight difference here, and one should keep that in mind. And it's good to probably alert the students to this subtlety. Then, of course, there are approximations for the low frequency, approximations of the high frequency end. Low frequency is the which means longer wavelength, is a Rayleigh-Jeans part. There, it can be approximated when nu is low, nu is small, h nu is small with respect to kT. Then the exponential can be approximated, and this is how the approximation goes. It's useful to remember then, in this case, for a given temperature, B nu is proportional to nu square. So this goes as nu square. These are the approximate, scaling laws, and it's useful to for the students to also remember that in the low frequency part, it goes as lambda square, nu square, or 1 over lambda square for a given temperature. And in the Wien's part, of course, it goes as, this is an exponential drop depending on the temperature because of this term. Now, so this is the spectrum, and then one can integrate this over the frequency range, because black body is an object which is radiating in all wavelengths. Remember, this is how it is derived also, right? All nodes and all wavelengths are excited. And so all wavelengths are present here. So one can then integrate over all frequencies, and then find out. So this was energy per unit time per unit length square per unit area per frequency per steradian. So if I integrate over all frequencies, then the per frequency part will go away, and then this is an integral in terms of the fundamental constants, and it goes as, it scales as t to the power 4. Right? So this is how, and all these constants are then collected. So this is sigma. Sigma is the Stefan Boltzmann constant, sigma by pi, and t to the power 4. Then remember, we had defined, this is just the specific intensity, as I have been telling you. The B is nothing but the specific intensity, but for the case of black body in particular. So we can define radiation energy density. So that will be 4 pi over c times B nu. And so the radiation energy density is then can be written as another constant, which is called the Stefan's constant, A times t to the power 4, where A is nothing but is related to the Stefan Boltzmann constant, right? And so this is the radiation energy density, A times t to the power 4. So the radiation energy density scales as t to the power 4. These things will be important for us when we discuss the deep inside the physical state of deep inside the star. We can also remember, this is again per unit area, right? So we can also integrate over area, right? But then remember, we have to take the normal to the area. Whenever we talk about area, we need to take the normal, which is the dot product with the normal to the area. So this will introduce a factor of cos theta, and then d we can also integrate over all steradian. So which will give us which will give us then, if I integrate over all solid angle, this will give us the amount of energy that is coming out per unit time per unit area, right? So this is going to be the integrated flux through unit area. I've taken care of, if I integrate over all wavelength, all solid angle, sorry. So then the solid angle will, this will give us 2 pi, and then this is sine theta d theta, and this is a easy integral. And then there's a factor of pi bt, which then you write it in terms of, remember the b integrated over all frequencies was sigma over pi, so that pi cancels, and this is how we get the Stefan-Boltzmann law. The integrated flux through unit area, in other words, energy per unit time per unit area uh, is proportional, is equal to sigma t to the power 4. Then, for example, we look at the spectrum of the sun, and then suppose we ignore for the time being all these deviations and say, this is our roughly, it looks like if I assume that the sun is at a black body, then this is the temperature I would associate with it. And then I can write that if the sun is a spherical star, then since this is the energy radiated per unit time per unit area, then I'll have to multiply by area, surface area, which is 4 pi r solar square, this is our radius of the sun square, which will give us the solar luminosity. Right? That we will do that for other stars as well. Here I have written an effective. Effective means just that, as I said, I'm going to ignore some of these deviations for the time being, and I would say that most of the spectrum, I seem to be able to fit a black body pretty well. So I would take that temperature for which for that black body curve, which seems to fit the observed spectrum over a range of temperatures, and then I'll call it an effective temperature. Of course, writing that effective also means that there are deviations, etc. Okay. Then we need to talk about what happens to radiation when it interacts with matter. Because if I want to talk about what happens deep inside the stars and outside the star, in the outer layers of the stars, then and the deviations that is caused, which disturbs the equilibrium, etc., etc., I need to talk about how radiation interacts with matter as it passes through matter and comes towards us. So this is very important for astronomy, because we are sitting on Earth and I'm looking at a star which is far away, just radiating, and photons are coming, and it is coming through all kinds of media. I don't know what is there in the intervening media, right? It can be part of the star, then this matter between the stars, etc., etc., right? So in order to make sense of whatever my detector is measuring, and in order to make sense of that and say that this is the radiation that is coming from the star, I have to understand how radiation interacts with matter. And this is this topic is called the radiation transfer. So I would like to, this is very important, and just please bear with me. I promise that at the end of this, we will have a good understanding of why there is a deviation and why is you see absorption and emission at a certain. So just bear with me the derivation of this, because if I just give you the final equation, the fun, then it will live like a magic, and we should not do that. Okay, so suppose I have some radiation, again in terms of the specific intensity, right? Because I know along a ray, if there is no absorption, no scattering, then specific intensity remains constant. So that's the important parameter. That's the convenient parameter that we should be looking at. So I take a ray of light, along which the specific intensity is given by I nu, which means I have a certain frequency in mind. And then it passes through, say, a cylinder full of some material, right? Schematically, I'm showing like this. And let's say after it emerges out of the cylinder, the radiation, the specific intensity is changed by an amount di omega, di nu. And this can be minus, that can be plus, I don't know yet. But let's say this is deviate. There's some deviation that I expect. The deviation could be because some amount of radiation has been absorbed by the material here. It also can be that the material inside this is also radiating. So it's adding to the radiation that is coming here. So both possibilities are there. Now, let's say the dimensions of this cylinder. It's, let's say, the length along the ray of light is ds. So S is the parameter that I'll be using as denoting the length along the ray. And suppose the area is dA, capital A. So the volume of the cylinder is dA times ds, and this is dV. Now, let us say I define a quantity called J nu, which I'll call it emissivity. This will denote the emitting power, the emissivity of the matter in this volume. So this emission from this matter in this volume will add to the radiation that is falling on this side. So the energy that will be added uh, will be will be proportional to the total volume of this object cylinder, total solid angle, total time, and the d nu, the frequency range, and the proportionality constant will be what I will call emissivity, right? And so this is the amount of energy that will be added. Remember, this is how we had defined our specific intensity. dE passing through an area is normal, right? Normal to the areas, and we have been taking it normal. So I knew dA, dt, dA. So, right. So this will be added to this energy. This is what is coming inside through this area, and this will be added. Now, what I've done, this dV I have broken into dA times ds, right? And I have conveniently took this. I've taken this combination out, so that this combination is something left outward outside the bracket, to make it look like this. Okay, so that, which means I'll be adding this amount of specific intensity. The above this, there will be something added to this, which will be equal to J nu times ds. Is that clear? So this di omega nu, the extra radiation that I'll be getting from this volume, will be nothing but J nu times ds. Because you see, if you compare this with this is the addition, and so you just instead of I nu, I'll have a quantity which is I nu plus this. So this is what is added. Or I can write it a differential equation. D I nu ds as along the ray is equal to J nu, which I can integrate. So suppose I call this S naught, and then from S naught to S, I'll have to just then integrate this J nu, and S prime is a dummy variable along this line of sight, and this I have to basically integrate from this point to this point, which is S naught to S, and then I'll get whatever the extra whatever the specific intensity as it is coming out of the cylinder, and this is the specific intensity as it is falling on the cylinder, right? This is the addition. Is that clear up till this point? Please let me know.
Sir, that means that di nu is the integral part. Is it okay?
Well, this is the differential amount that I'm adding to I nu, because these are all differential volumes, small volumes, right? These are small volumes that I've taken, dV. So this is the extra term that I should add to the specific intensity. This is the total energy that is entering the volume. This is the extra energy that is being emitted by the matter in the volume. So if you compare this with this, I'm adding this part. So this is the part that that is being added, right? So the extra part is nothing but J nu times ds. And so this is a differential equation. And you can find that, so when you integrate, of course, the a solution of the differential equation will be given by the integral. Is that what you mean?
Yes, yes. No, no. I was just no. It is okay now. I was just a
Yeah.
little
Okay.
bit confused with that. Now.
Is
It
that,
is
is
okay
that
now.
okay now?
Yes,
Okay,
yes,
fine.
yes, yes.
I hope it is clear to others also. Yeah. So I'll move on to the next possibility, that that uh, yes, that now there can be absorption because of the matter in the cylinder, which will subtract from the radiation that is following on it. Now, let us see. It will depend on what kind of matter that is, what kind of interaction are you one is talking about. So let's say there are number density of observers, which can be atoms, which can be free electrons, whatever it is, right? Let's call it just observers for the time being. So n is the number per unit volume, number density, number per unit volume. And say the cross section of interaction, whatever the interaction is sigma nu, which is of course going to be dependent on frequency. So let's see. Then the total area of the observers, the total area that will be put in front of the light falling on it is going to be n times dA ds. This is the total volume. So this is number per unit volume. I'm multiplying by the volume. So I'll get the total number and then multiply by the cross section for each observer. So that will be the total area that will be blocked by the observers. Let's think in terms of the fraction of the area that is blocked. I can say that there's the fraction of the light that is going to be absorbed, fraction of radiation that is going to be absorbed. Right? So the fraction of area that is blocked is this divided by dA. dA is the total area, and the area that is being offered as resistance to the radiation is this. So the fraction is this. Then I can say that, okay, this will be the fraction of radiation that will go away from my I nu. So that will be, there will be a negative sign here, right? And as you can see, this is dA will cancel out. It will not depend on the area, and this will depend on the ds. In other words, I can then write an equation. di nu is going to be minus n times this like this. I'm going to define something called absorption coefficient, right? By combining these two, number density of observers and the cross section, and multiply them, which will have the dimension of per unit length. I'll call it absorption coefficient, right? So this will have the dimension of per unit length. I can also define something called opacity, which this is how I'm going to write opacity. That this absorption coefficient is then written in terms of this kappa nu, and rho is the mass density. And then kappa nu will have the dimensions of length square per unit mass. Now, this is useful in the sense I can talk about, say, okay, this much of kg of matter will offer this much of length square or area of cross section. Okay, this will be meter square per kg, for example, or centimeter square per gram. And one can think that, okay, 1 kg of matter offers this much of blocked area. Okay, for example, if now we have certain particular interaction in mind, let's say it's ionized matter, then let's say it's just free electron, and I have Thomson scattering in mind, right? So then I'll use Thomson cross section. So this is in CGS unit. This is the sigma t, Thomson cross section. Then I can write the opacity, this kappa nu, in terms of number density and the mass density, and that will depend on, that will be like this, centimeter squared per gram. In other words, if I have 1 gram of matter, the light is passing through 1 gram of matter, then this will be the combined cross section that is offered to, cross section or resistance, right, of absorption. So it's useful to remember some of these numbers, which will might be useful later, because when we talk about stellar interiors, for example. Okay, so we have then two cases. One, we had in there was this term, which was because of radiation being have an extra term because of matter in this intervening matter radiating by itself, and then the intervening matter can absorb, then there'll be a negative term. Combining these two terms, then I have an equation which will tell me how is the radiation, the specific intensity is going to change as it passes through intervening media. This term because of the radiation from the intervening media, this is because of absorption. Okay, I can then take the ds out, and then this is a differential equation, then I can write. Right? This is the basic equation of radiation transfer. In order to proceed, we can define something called optical depth. This is going to be an important concept, which we denote by tau. And I'll define as d tau. Again, these are all functions of frequency. Okay, this is not independent of frequency. So d tau nu is, I'm going to define as alpha nu, which is the absorption coefficient times ds. If I do that, and I also define something called a source function, capital S, not small s. Small s I'm going to reserve for only the length along the ray of light. Capital S nu, I'm going to define as the ratio between this emissivity and the absorption coefficient. I'm going to call it a source function. And I'm sure it's ringing a bell in your mind, because this is going to look like, Kirchhoff's law, the emissivity and absorption coefficient, and we're going there. So suppose I define a source function like this and define d tau, then I can write this differential equation in a very compact form. So this ds, I'm going to write it as d tau, and this is going to be now s nu minus I nu. And this is the equation that I'm going to worry about. Are you with me at this point? And I'm going to ask you again to just bear with me, just be a little bit patient. I know that it may be slightly, uh, it may be something new, and it's not an easy concept at all. But at the end of, say, if you just give me 10 or 15 minutes more, I will show that this is a good way of explaining why there are deviations in bars. Just give me 10, 15 minutes more, and we will try to solve this equation. And I don't want to write the solution in a PowerPoint slide, because then it will again, look like a magical thing. And let me then turn on my tab, and then I'll stop share here. So the equation I had was this, right? D I nu, and I hope you can, this is d tau nu, right, equal to S nu, this is the source function, and this is the I nu. This is my basic equation of radiation transfer. An optical depth is something, and I have written that d tau nu is equal to alpha nu times ds. In other words, tau nu as a function of S will be an integral of alpha nu, which may be a function of location. So I'm going to define a dummy variable and the location, and starting from, say, when the optical depth is 0, S is equal to 0 to S. Right? This is my total optical depth suffered by the light as it passes through this volume of matter. So here I had I nu, and then here I have I nu plus d I nu. Right. Okay, and this is the length. S is equal to 0 here, S prime is 0 here, and S prime is S here. Right? This is my dummy variable. Am I clear on this point? Now I'm going to call this matter transparent when tau nu is less than 1. I'll call it transparent. And when tau nu is more than 1, I'll call it opaque. Okay. Okay. Now this equation, as you can see, it's not a very difficult differential equation. Um, we can multiply. So let me just bring this term on to the other side. So then I'll have I nu plus d I nu d tau nu, and this is S nu. And then I'm going to multiply both sides by, remember this method called multiplying by the integrating factor. And I'm going to multiply both sides by this factor, e to the power tau nu. Once I do that, this is going to be a total differential of, it's, as you can see, this is nothing but a differential of this. Are you convinced? Because if I take a differential of this, I'll get this. For one term, I'll have the exponential term. I'll work on the exponential, take the derivative of the exponential term, and then leave this. And then so the next one, second term, I'll take a differential of this, which will give me this, and then the exponential term will remain the same. You agree with me, right? This is the standard way of solving this kind of differential equation. So once I have this, I can just integrate between tau nu of 0 and whatever the tau, right? And so I'll have I'll write the equation here. In other words, if I integrate between, so integrate between tau nu prime 0 and tau nu prime tau nu, I mean, I'm just writing it formally so that I'm just integrating this, right? So for one thing, I'll have e to the power tau nu I nu at tau nu, and minus, because I'm integrating between this and this. So this term will give me e to the power 0, which is 1. So this term will be 1, and I'll have I nu at 0. Sorry, this is 0. And on the right hand side, I will have an integral of tau nu S nu. This is S nu. So I'm basically integrating this. S nu will be a function of the local variable that I've taken, which is tau nu prime, which means tau nu prime is what? What is the total optical depth from here to here? And e to the power tau nu prime d tau nu prime. Now this is a formal solution of the differential equation which we have written down here, right? This is the formal solution. Let me tidy it up a little bit, and then so it will look nicer. Let me erase this, and then let me then write it again. So basically, I'll take the I nu, which is coming out of the cylinder, will be equal to I nu that is falling on the cylinder times e to the power minus I, plus this material. This is the term that I'm going to be adding, which comes out of the cylindrical, the matter in the cylinder, and this is this, and e to the power tau nu minus tau nu prime d tau nu. This is exactly the same thing that I have written, by the way. So the last thing I had before I erased, I had this equation written. I should have kept that so that this doesn't. So this is the term. Sorry, this is what I had on the board. And so before I had erased, this is what I had. So what I've done, basically, I have divided the whole thing by e to the power tau nu, which is why you get this term here. And I have taken this term to this side. So that's it. So I have done two things. I've just taken this term to this side and divided the whole thing by e to the power tau nu, which will give me this. this. And this is my solution to a formal solution to the radiation transfer equation. Now, this looks very, very, very difficult, but it is not. Let me assure you that it's actually, it makes sense. So let's try to make sense physically. What is happening here? You see, what we had, the physical picture we had is this. This is the intervening material we had, and this is what was falling on the. So this is the radiation that is falling on one side of the material, and that is coming out after it has suffered whatever interaction it has, right? And so what is it saying is that, let's see this first term. What is this saying? That the incident radiation is going to be attenuated, is going to decrease by a factor exponential to the power minus minus tau nu. And remember, tau nu is, it's an integral over the absorption coefficient at different points of the light ray as it is passing through, right? So the first term is nothing but saying that the incident ray is going to be decreased, attenuated. Something is going to be subtracted, and the subtraction will depend exponentially, and this depends on the absorption coefficient, etc., etc. Makes sense, right? This is what we expect. But what are the other terms? There's going to be some other term also, which is what? Now, this is the source function, means, remember, source function was nothing but J nu divided by alpha nu. In other words, see, as the light ray is coming, there's going to be addition of photons from the matter in the cylinder itself, and that is what it is showing. But this, for example, matter here is radiating some extra photons, but that photon will be also absorbed by the rest of the material. This is the rest of the material. It's going to be also whatever the matter itself is radiating will be absorbed by the rest of the material as the light ray is coming out, and that is what it is doing. This is the subtraction, means basically this part only, not this part, because the light ray is coming towards us, right? So again, to sum up, there are going to be two terms. One is that incident radiation is going to be there is going to be some absorption throughout the volume, so there will be an attenuation. Plus, there is going to be some extra photons coming from the matter itself, which will be appropriately absorbed out by the rest of the wave. Okay. Now, okay, so this is the formal solution, and does it make sense? I mean, I've tried to explain this sort of complicated looking equation physically, and I think it makes sense. What would you say? Any comment or any questions?
Yes? Sir, I have a question.
Yes, please.
We talked about this reduction in the radiation, but are there like we are talking about interaction between matter and radiation? So is there a possibility of this stimulation emission taking place and it may increase the intensity?
Yes, all kinds of things, but which are all hidden. I have not actually told you what is this value of this, right? So when you have a two-level atom, for example, so there will be stimulated emission. So there will be stimulated, there will be alpha nu because of stimulated emission, which you will have to then write it in terms of those two levels atoms. You'll have to write that out. But this is a very general statement that I'm making.
Okay.
It can be due to atoms. It can be due to any kind of interaction. Whatever interaction you give me, I can then, in terms of this scattering, the cross section, I can write an absorption coefficient. You're right.
Okay.
If there's no question, then let me move forward.
Sir, I have a question, sir.
Yeah.
Sir, in the second term, in these two terms, in the second term, the S nu, there's also a term e to the power plus Z nu prime. But can I compare this to I nu? I mean, you said that. Okay, sir, you said that S nu is equal to J nu by alpha nu.
Yes.
This is kind of a source of some radiation inside this volume. But there's also another term, e to the power plus z nu prime, which is the dummy.
Okay, this is tau, by the way.
Tau nu prime. Sorry,
tau, yeah.
Tau nu e to the power plus tau nu prime, which is the in the previous part. I nu 0 e to the power minus tau nu. There's no tau nu prime, so e to the power.
because there's no integration here, right? There's no integration here. Right. So tau nu prime is basically a dummy variable here. Sorry, it's a dummy variable to tell you tau nu here, from here to here it's tau nu. From here to here is tau nu prime. From here to here is tau nu prime, depending on wherever that S prime is. So S prime is the dummy variable which goes from 0 here to S here. And so the tau nu also goes from, so tau nu here is 0, and tau nu here is tau nu, it is, right? And at any other intervening material, it's tau nu prime, which will be basically the integral from
initial term is
right? Okay, let's move on.
Sir, I just wanted to ask you one thing. This is the cumulative effect of both the absorption and emission inside the volume.
Yes.
Yeah. What will be the cases if there is only absorption or only emission?
We will do. Yes. So let's look at this. Exactly. Very nice. So let me clear this out, and then let's then look at some of these terms, some of these limits, right? Where we have expression like this, and as you were saying, that suppose there is no absorption, suppose there is no only things like that. So before that, let's simplify a little bit. Let's say that the source function is constant. Okay, throughout the volume. Let's simplify our life and say that.
Sir, one thing I'd like to ask.
Yes.
This means said tau nu, value of tau nu will be 0 to 1.
No. Tau nu going from here, tau nu is equal to 0, and here tau nu is equal to tau nu. Actually, I should write tau nu prime is 0. So tau nu prime is the dummy variable along the ray.
Now you wrote somewhere that tau nu, when tau nu greater than 1, then it is opaque.
Yes.
That means light will be not propagate after that.
We'll come to that.
It seems to me that tau nu will be 0 to 1.
No, tau nu can be much more than 1 also. Tau nu can be much more than 1. Just give me 2 minutes and I'll come to that. Okay. So let's simplify our life a little bit. Let's say this S nu is constant. Okay. Then I have a slightly simpler equation. Okay. And then I'll write it like this. So I knew what is falling on the material, and then it is getting attenuated. And then let me take the S nu out, and then this can be easily integrated, and this will give me e to the power I nu like this. If S nu is constant, it's uniform. Now let's say tau is very, very large, very, very large. Let's say it's infinity. Okay, let's say it's infinity. Then what will happen? I nu will then tend to S nu. See, this term will then go to 0, and this term will go to 0, but this term will remain. So I nu will tend to S nu. It's not that. So what will happen? I will not get any radiation that is coming from here. I will only see this material, whatever that source function is, right? I will not see the background object. I will see only whatever the matter is in the foreground. It is shining so bright because its optical depth is very large. I'll only see that. I'll not see the background. Makes sense? If say the tau nu is very, very small, let's say in the limit of tau nu going towards 0, then what will happen? I nu basically will then go towards I nu at 0, and this will be basically 1. So I'll get whatever is coming out, and then some material, some amount of radiation that is coming out of this. But this, if tau is 0, then I'll basically see whatever the background object is. which means what? If the tau nu is 0, then the intervening material is not posing any resistance to the background object, and I'll see the total background object as it is, right? Now, okay, then we can also talk about other limits. We can clear this, and let's see, there is only absorption and no emission. So if there is no emission, then I will not have this thing. So if there is no emission, only absorption. Let me light it, because this is going to be important. Only absorption, which will mean I knew that I will get, right? E will be equal to I knew that is falling on it times this, which means there is going to be attenuation of radiation by a factor e to the power minus tau. And if tau is equal to 1, then basically the radiation will be decreased by a factor of 1 over E. 1 over E is, it's like what? It's like 50% taken away, right? 1 over E is it's of the order of 0.3, so 60% is taken away, right? So let's say, you know, a major portion of the radiation will be taken away, will be attenuated, not totally opaque, right? So tau is equal to 1 means radiation is attenuated by a factor of 1 over E. Right? So this is about 60% gone. Right? So which means what? If this material offers a resistance, optical depth of 1, then this is the probability of light that is coming that is going to come out of this. 1 over E is the probability of light that the light will actually emerge out of this and come towards me. I can say that, right? 1 over E is the probability of light that is going to emerge out of a material which offers optical depth of 1. We can remember this. Which means what? Remember, let's go back to our stars case. Okay, now here let me also then say that if now matter is in thermal equilibrium, if matter is in thermal equilibrium, if this matter here is thermal equilibrium, then I will write S is basically going to be the black body, right? This is Kirchhoff's law, right? If it is in thermal equilibrium. If this matter is in thermal equilibrium, then S nu will be equal to B nu, right? So let's talk about that case only, okay? I'll erase this and then let me get clear. So then I'll have, so basically I'll have an equation which is going to look like this. So suppose now I talk about a radiation passing through matter which is in thermal equilibrium, right? So di nu, this is, I'm going to write this equation again just to, so that you know, you look at it. So some matter radiation is being absorbed out, and instead of source function, now I'll have a black body radiation which will depend on the temperature, local temperature, right? And as we have solved, and I'll just write the final solution in a slightly different way, but it's not in a slightly different way. So I'm going to take B out here, all right? And I'll take the other terms here. So this is falling on the other side of the radiation. That is, so this is the solution that I had written. I just rearranged it in a slightly different way. All right? Which means what? If tau is very large, very large, then this term will go away. And I'll get only this. Which means what? That's the blackbody radiation. Remember, we've been saying that what is blackbody radiation? When matter is in thermal equilibrium, right? Then the radiation that I get is blackbody radiation. Which means what? The optical depth is very, very large. And I say that this is going to happen only deep inside the star. And we will actually quantify this. Now we have, we know how to quantify this sort of things, because we'll talk about absorption coefficient, opacity, etc., etc. So next time we'll discuss all this. But this is very clear. If the opacity is large, the optical depth is large, then the radiation is black body, right? And if opacity is, say, so let's talk about the star, right? We had this stellar structure. Deep inside the star, opacity is very, very large, very, very large. Let's say infinity. But here, near the surface, opacity, there is going to be a place where opacity is equal to 1, roughly equal to 1. This will then offer a probability for the photons, a 60% probability for the photons, or 50%, to escape. And that is what we call the photosphere. When we look at the sun, we are actually looking at a surface layer where the optical depth is of the order of unity. And that is allowing the light to escape. Some, 1 over E, so it's going to be decreased by 1 over E. That's the probability. And that is called the photosphere. So deep inside the star, optical depth is very, very large. As I go towards the outer layers, optical depth decreases. And as soon as I hit something like optical depth of 1, there is a substantial fraction probability for the photons to escape. And that's what we see. I really want to get to the point that where I can show you that the deviation can be of two kinds. Now, suppose, before that, I need to talk about, suppose there's a background star here, and there's some material here, and the light ray is coming. And so this is a nebula. So it's a diffuse gaseous nebula. And see, the optical depth is 1, less than 1. So it's transparent, more or less transparent. It's letting the most of the light reach us. And let me also say that this is a function of the frequency. And let's say this matter is in thermal equilibrium with itself. So S nu is equal to B nu, which is the black body at a different temperature. So the radiation transfer equation then allows me to write the, after coming out of this intervening medium, the incident radiation is going to be attenuated by a factor which is e to the power minus I nu. And then this source function, which is now I'm calling it just black body, is going to be appropriately also absorbed out. Now I'm going to, since optical depth is less than 1, I'm going to make some approximations, and I'm going to, okay, let me first write it. Let's say there is no light here. Let's say I nu is I0 is 0. Suppose there is no light here. Okay, only I'm looking at the gaseous nebula. Then what's going to happen? I nu, whatever I'm going to get is basically from this object itself. And if the tau nu is small than 1, I can make some approximation, and I'm going to say that this is basically, if tau nu is small, I can expand it out, and then this term will be 0, and then basically I'll be saying that it'll be this. Which means what? Which means I will see a positive radiation whenever tau nu is large. Remember, what is tau nu? Tau nu is nothing but alpha nu times ds, or this is d tau nu. In other words, I nu is going to be proportional to alpha nu times b nu, right? Because tau nu is proportional to alpha nu, and so my radiation that I'll be getting will be proportional to alpha nu. In other words, wherever the absorption is large, I will see a positive emission. Remember, I'm not looking at any background star. I'm just looking at this nebula. And what I've assumed is that the nebula is optically thin, it's transparent, and it is in thermal equilibrium with itself. In that case, what I'll see positive increment in the I nu will have, there will be spikes whenever alpha is very large. And where is alpha large? At the spectral lines. Remember the spectral lines, the cross-section of interaction with the photon. For example, I have an atom here, and there are different, levels. And for a photon of a given frequency, so this is the energy level, say n is equal to 1, 2, 3. So for a given frequency, if the frequency happens to be just right for a spectral line, then alpha, the cross section will be very large. It will get absorbed out, right? So alpha nu is large at the spectral line. So what you'll see is nothing but in frequency space, you'll see emission line. This is what you'll get. So you'll basically see a lot of emission whenever there is a spectral line. So these are emission line spectra. You actually see that from nebulae. Okay. And I'll come that you also see, I'll come to this, where do you see in the case of sun also? This is clear. So I just want to make this point that tau is related to alpha. Alpha is related to the cross-section of absorption or interaction between photon and matter, and that depends on the spectral, the energy structure of different atoms in different ions. Okay, now let me come to this most interesting case. So I want to make a model of a star, and I'll say that I have a star in mind, a model of a star, where I have two parts of the star. One that I call inner star at a temperature, say Ti, and I have an atmosphere, outer layer, which is, I'm going to call it, which is a different temperature, T out, TO. It's a very simple model of a star. Okay. And suppose this is in thermal equilibrium, the whole star is in local thermal equilibrium, so that S nu is equal to B nu everywhere. Okay? Now, but I have a basically two layer kind of a model. It's a two temperature model, the inner temperature and the outer temperature. Very simplified model. Let's see what do I expect of the radiation from this object. All right. So I knew, now I know how to do all this because we have solved the radiation transfer equation, and I'll write it out again. If I keep writing, so this is the initial, this is the light that is, so I want to see what is the light that is coming out of the outer radius. And suppose this is what I call the radiation that is falling on this medium. All right, and so B nu 1 minus e to the power. That is the solution we had. Now this is what I'm saying is the radiation that is falling on the inner side of the atmosphere. So this must be then just the blackbody radiation of the inner temperature object, and right. So this is nothing but the blackbody radiation at the inner temperature. And this is going to, this basically stays the same. And this is now the blackbody radiation of the outer layer. So I'm going to be slightly more specific here, and then say this is this. Okay. Now let's see what is happening. Let's say tau is small. It's not very large. So the atmosphere is allowing the radiation to pass through. All right, so it's small. Okay, which means I'm going to make some approximations here, and I'm going to write B nu Ti, and this I'm going to write as 1 minus tau. The exponential I'm going to write it, and this I'm going to write as basically tau. This is okay, and I'm going to then write it like I'm going to gather two terms. I'm going to keep this separate, and I'm going to take these two terms, and this is important. Look at this. Just look at this. I have just rearranged this term. What does it tell? that I'm going to see the blackbody radiation that is coming out of the inner star, the inside. But there's going to be some deviations here. This deviation is caused by the optical depth of this atmosphere, the outer layer, right? And the deviation, the sign of the deviation, whether it's going to be minus or plus, will depend on the relative temperature of T0 and Ti. Suppose I have the outer temperature less than the inner temperature. In that case, I know that the blackbody curve, do you remember? The blackbody curves are like this, and at a higher temperature, I have this. This peak has shifted to higher frequency, right? But the whole curve has also shifted up, right? So if T0 is, this is say T0, and this is Ti. If Ti is larger, then what will happen? If Ti is larger, then this is going to be negative. In other words, if the outer layer of the sun is at a lower temperature than the inner sun, then there will be subtractions. And where do you get subtraction most? Oh, this is new. Where do you get most of the subtraction? Wherever tau is large. And where is tau large? Tau is proportional to alpha nu, which means at the spectral lines, right? And wherever, if Ti happens to be larger than if To is larger than, for some reason, if the atmosphere is hotter than the inner temperature, then you'll be positive, which means, again, you'll see emission lines. Because, and here you will see absorption lines. Do you agree with me? Is this clear? I've just inferred this from this equation. And I made a 2-temperature model of a star, and where I have an inner star and an outer layer. And depending on, so first of all, I have proved that had there been no, because of, there's going to be deviation because of the atmosphere, and the deviation can be of two kinds, depending on the relative temperature of the outer layer with respect to the inner layer. If the outer layer is cooler, then you will see negative deviation, which means you will see absorption lines. And if the outer layer is hotter, then you'll see emission lines. Is that clear?
Hello, sir.
Yes.
Yeah. I have just some confusions.
Yes.
This you are comparing the optical depth. It's proportional to the absorption coefficients.
Yes.
Yeah. And then you are.
That's how I had defined.
See, yes. And the absorption coefficients, you were connecting it with the spectral lines.
Yes.
See, that connection of the spectral lines with the absorption coefficients, that part I have not just understood.
Okay. Okay, let's see. So the absorption coefficient, as somebody was talking about the stimulated emission, etc., it will depend on the type of interaction one is talking about. So suppose I have atoms and then the different energy levels. Then, as you know, that suppose a photon comes, and the photon has the exactly the same wavelength depending on the energy level difference.
Yes.
Then it will get absorbed, right? And basically, what is happening, if you look at the absorption coefficient, the absorption cross section as a function of that absorption coefficient has got basically spikes, or these are resonant lines. We call it resonant lines. So whenever the photon frequency has such an h nu, the energy is equal to the energy level difference, then there is resonance.
Yes.
and the cross section of absorption is very, very large, which means it gets absorbed.
Yes.
So that's what I meant. If the absorption coefficient is large at these spectral lines, then this is directly proportional to the absorption coefficient, and this is directly proportional to this. So tau is also large.
Okay.
Okay.
Okay. Yeah. Yeah. Thank you.
So if this is clear, then I'll go back to the slides I had.
Sir,
yes, please.
One question. I mean, in this model of the star, you have shown the inner temperature is Ti and outer temperature T naught or TO.
Yes. Yeah.
Now, in the normal star, outer layers are always, I mean, outer temperature are always lower.
Oh, we're coming there. Okay, fine. Go on with the question.
I mean, does it mean that we'll always have this negative this term?
No. So that's why I want to go back. So, but before I go back to my slides, I want to just make this point. See, this was realized in 1859 by Kirchhoff. Kirchhoff actually had done this, and he realized this. And before 1859, the model of the sun was that it was a very cold interior, and the outside layer was hot. That was the model of the sun, and that was the model of the sun, for example, proposed by William Herschel, the discoverer of Uranus. And his model was that the sun is cold in the center and it's hot outside. And whenever you see a sunspot, for example, this is basically, in his model, there is a hole in the surface of the sun, which is allowing you to look at the very cold, which has been dark interior. That was the model of the sun. And what Kirchhoff said, well, I don't think that is correct. I think it makes more sense to have a hot interior and a cool atmosphere, right? But remember, we have been saying that this layer is also in thermal equilibrium. This is also in thermal equilibrium, so that this is the source function we have written like this. So, but then people said, Kirchhoff, you are wrong. I mean, what you're saying doesn't make sense, because if this is in thermal equilibrium, then I should be seeing emission lines from this area also, this part also, but I don't see. But then Kirchhoff said, well, you have not actually subtracted out the whole sun. What you're seeing is the whole sun, and then what you should be doing is to isolate only the outer part of the sun. And people said, how can you do that? Then people realized that, well, wait for a few years. 1868, there's going to be a total solar eclipse, which will allow us to isolate the very outer surface of the sun. And then we'll check whether Kirchhoff is correct or not. And everybody was basically, that was a test of Kirchhoff's law. And as you know, 1868 solar eclipse was visible mostly from India and Southeast Asia. And people had come here. And that's where people actually could isolate the outer part of the sun and see that, yes, you do see emission lines if you just look at the outer part of the sun. So it is also in thermal equilibrium. And if you can isolate the most of the sun, I mean, during eclipse, of course, this is all hidden out, and you can see the outer part, and you can see the spectrum of the light from there, an emission line, and that is how helium was discovered. So first of all, Kirchhoff was proved correct. Helium was discovered. This is 1868 solar eclipse. So this is very, very exciting. Initially, people thought sun was cold in the interior and hot outside. And then Kirchhoff, in 1859, he suggested this. And then it was proved in 1868. But then just allow me to go back to my keynote here. So remember this the spectrum we had. Yes. So can you see my slide?
Sir.
Yes. So
Yes.
you see. So you see absorption lines here, but you do see emission lines here, which means what? As I think, is it Dr. Abhijit Das? You were saying that does it mean that the outer temperature is lower? But yes, that is true. Outer temperature is lower. But isn't there also a hint that something else is happening here? You see emission lines. Where is that coming from? So which means there is an outer layer even beyond the photosphere, which is hotter.
I see, sir.
Yes, and that is corona.
I see.
Yes. You see, so see, if I had just said this, and then it wouldn't have made sense. And then now that since I have actually solved the radiation transfer equation, suddenly even a simple 2-temperature model of a star makes sense. But you realize that this immediately tells us that there is a hotter, beyond this, there is a hotter layer, which is the corona. It can be as hot as it can be as.
I have a question.
Yes.
Does sunspot affect the emissivity of the solar system? The radiation emitted from the solar system?
You mean the sun, not the solar system, and as a whole,
No.
the solar system, just from the sun?
No, sir. Sunspot.
Yes, I understand that sunspot, the emissivity, the local emissivity is very different. Yes, you are right, because it is cooler. And maybe in the next class or the next class, we will talk about the sunspot. It's a very important question. Yeah.
Okay, thank you.
So there is there is some difference between the emissivity of the sun in different locations. In some places, it is cooler, so the emissivity is lower, which is why we see it less bright. But I just want to make this point here that this immediately tells us that there is a hotter layer here, very far outside the sun, as hot as 1,000,000 degrees. So the photosphere, remember, photosphere is at 5,700 degrees, but then there is a layer of the sun which is much hotter than that, and that's the corona. And if you anybody of you who have seen a total solar eclipse, you would realize that. Have you seen? Has any of you seen the total solar eclipse? The corona is blazing. Only during the total solar eclipse, you can see the corona.
Yes, sir. The temperature of the corona will be higher than the outer layer, right, sir?
Yes. So this is like 5,700 degrees at the year, and the corona then heats up. Okay. Now there's another question: why is it so? We'll discuss. We'll continue this. Right, and I hope I'm sorry that I have taken such a long time to come to this conclusion, but I wanted to actually do this quantitatively and not just with words, because we are physicists, and I think this makes sense after we have talked about radiation transfer. Yes.
So yeah, just this is something, sir, really beautiful, that the observation of the emission lines and comparing it with the radiative transfer equations, it tells that yes, the
absolutely,
sun
isn't it?
It's atmosphere. This is just beautiful.
Yes.
And
thank you for your patience that you just stood out with me, because I wanted to make this point at this. Thank you. Okay.
Thank you, sir. Yeah.
Thank you, sir.
So thank you, sir. Sir, you had mentioned a couple of books you will mention.
Right. Okay. So there is a book off the top of my head. There is a new book that I have been liking it a lot, by Dan Mause. I forget the name of this book. I'll put it in next time when we meet. I'll give you the book. But it's called by Dan Mause. The last name is Maoz. And I like this book very much because it is perfectly targeted towards BSc sort of physics core honors students who may be interested in astronomy. And he talks about the physics of it. And of course, there is a very classic book by Frank Schuh called Physical Universe, which is a classic book. It has been around for a long time, which also discusses these sort of things from a physicist's point of view. So I can think of these two books off the top of my head, but next time we meet, I'll have maybe I can think of other books as well. From Raghavendran, asking what could be the mechanism of heating of this layer? $1 million question. And this is an open question. What heats up the corona? Why is it so hot? And well, I mean, people are still working on this. There are ideas. There are plasma effects, for example. So maybe we'll talk about this later, right? I mean, we have already reached about 8 o'clock. But it's a very, very interesting and important question. And as I said, this is a matter of research. I'm not an expert on this, but I can just talk about
so yeah, I would just like to say something on it, just because I did my PhD on solar astrophysics. So yeah, it is mainly the MHD wave heating. One is, and second is the magnetic reconnections also. But again, so far we do not have a dominant mechanism. Like wave heating, it contributes a bit. Then magnetic reconnection, it contributes a bit. But so far we do not have a dominant mechanism.
Right, there you go. This is still a topic of research.
Yes.
So maybe next time you can actually explain what this magnetic reconnection is. Others may want to hear. So maybe we'll talk about it.
Okay.
Right? Thank you.